Good afternoon, data managers. I am going to take a brief look at measures of variability part 2, and I'm going to do the first half of this. I'm going to do this as a two-parter, so I guess you've got 3 total for variability. We'll take a look at the terms and definitions first. And what we did last time is we looked at the range, we looked at the interpercentile range, and we also started with something called the deviation from the mean. And I'd like you to recall that the deviation from the mean adds up to 0. The total sum of that deviation from the mean is 0. With this lesson, I'm going to take a look at average deviation from the mean, variance, and standard deviation, and we're going to leave the coefficient of variation for a future date. So, I'd like you to recall from your earlier grades the absolute value of something. So whenever you use those vertical bars, it tells you that you're taking the absolute value of something, and we are only concerned with the positive values. So, happy baby today. In this case, whenever we're looking at all the real numbers, we're going to take the absolute value of x, and if x is greater than or equal to 0, we're going to take the value of x. However, if x is less than 0, we have to take the negative value of x, because a negative times a negative is a positive. Now, let's take a look at these examples. The absolute value of 5 is also equal to the negative of negative 5, and that ends up being 5. And the same if you take a longer series of numbers, negative 5 plus 11 minus 14 minus negative 2 minus 10, and you take the absolute value of all of that, you end up with a value that is equal to the absolute value of negative 16, which also happens to be equal to the negative of negative 16, which also happens to equal 16. Ultimately, your goal is to have every number ending up positive. Now, last time we looked at the deviation from the mean. This time we're looking at the average deviation from the mean, and what that is we're taking average magnitudes of the deviations from the mean. That means we're taking the absolute value, and we'll take a look down below at the bottom of the screen, and you'll notice that the sum of x minus x bar, and you'll notice that you're taking the absolute value of that difference and you're dividing it by the total number of objects in the sample. Or on the right hand side, we're looking at the population, where we're taking the sum of x minus the population mean, and we're taking the absolute value of that difference and dividing it by the total number of samples in the population. Now, let's take a look at the operations involved with average deviation from the mean. So we've got our pretty formula. We're taking a sum of the values, the difference of the value and the mean, and we're dividing it by the total number of objects in the sample. And remember, if you're dealing with x, you're dealing with the value of a single observation in the dataset. If you're dealing with x bar, that's the mean of the sample dataset. And remember, in this case, both cases, we're dealing with the samples. And then when we take the difference of the two values, we have to take the absolute value, and that is called the deviation from the mean. So, apologies for all the interruptions. I'm resuming again. This last item here that we have, the sum of the absolute value of x minus x bar, so that is going to add up all of the absolute values of the deviations from the mean. Our final result will be a positive number. You can never get a negative number out of this. And then, of course, the final variable in this equation will be, this formula is lowercase n, which is the total number of observations in our sample. So remember, all of this has to do with taking a sample from a population and applying statistical methods to it. Now here we have an example of a different formula. Why do we have this formula? The sum of the absolute magnitude of x minus mu all over capital N. Remember that we have a difference between the population and the sample, and that the population means that you're dealing with every single object, while the sample only deals with those objects that you actually took a look at. Sometimes you are able to take the entire population and apply statistics to it, but more often than not you're working with a sample of that population. So if you're looking at the population, you tend to use Greek letters like mu or capital N for the number of objects. Now, let's take a look at an example. We had banana computers last time round, and we took a look at 6 months worth of data. So we've taken the end of month stock value in dollars, and we've got them here ranging from $59 at the low end to $74 at the high end. Now our task here is to compute the average deviation from the mean, and we've got a nice formula here for the average deviation from the mean. And our formula is the familiar one that we've been working with, the sum of the absolute value of x minus x bar all over n. Now, in the first case, we know that our mean is 67. You might recall that from the last lesson. And what we have to do is take every single value and compare it to 67. So 70 minus 67, 3. Plus 62 minus 67, which in that case is negative 5. However, remember that you end up with positive 5. So, next line, 3 plus minus 5 plus minus 8 plus 1 plus 2 plus 7, all over 6. You get rid of all the negatives through the absolute value signs, and we end up with a final average deviation from the mean of about $4.33. $4.33 is our average deviation from the mean. Now, let's take a look at the next concept. Building on what we just looked at, we've got the variance. And we've got two formulas here. One on the left is our sample variance, and on our right is our population variance. Now, remember how we were taking average deviations from the mean and using the absolute magnitude signs? In this case, we're essentially doing the same thing. However, instead of using that operation, we are squaring the difference, which has the exact same effect, because if you square a positive number, you end up with a positive number. If you square a negative number, a negative difference, you end up with a positive value. So we deal with our problem of adding up to 0. This way we can compute a variance that gives us a good estimation of the variability of our data. So variance is the average squared deviation from the mean. Okay, was that thrilling or what? Now let's take a look at the terms. Average. So at the bottom of in the denominator of each of these formulas, we have the total number of objects. N minus 1 for the sample and capital N for the population. So remember, dividing the total sum of everything by the number of objects gives us an average. Next, we have the square. So remember, the square gets rid of our negative differences. Then we have the deviation, which is the deviation from the mean. So is this a pretty picture or what? We've got red, green, purple, and blue. And my apologies to any of you who are red-green colorblind. And here we've got a color-free version at the bottom for you to take a look at. If you wish, you can pause, take a moment to think about what you've seen, perhaps reread the course material. Okay, there are two other variance formulas I'd like to show you before giving an example. The variance of frequency grouping. So here we've got the formula, and it works very nicely because the variance for every single object that has the same value is going to be the same. You have the same difference. So x minus x bar, if x is 5 and x bar is 2, if you've got 5 5s, every single one of them is going to have the exact same difference, which would be 5 minus 2 is 3, squared is 9. So all you're doing is taking 5 times 9, and you've simplified it a little bit. And then the same thing at the bottom, the sum of f minus 1 or if you're dealing with a population, the sum of f. And the variance of frequency distributions, slightly different, because in that case you're not taking the actual value, but you're taking the midpoint of each class interval. Remember that we've got many examples in the past. One that we were looking at had a class interval of 10 to 20, 20 to 30, 30 to 40. So in that case, you'd be looking at the halfway point between 10 and 20, 15. So that's what the m represents in both cases here. So essentially the same thing as what we were just looking at, except rather than having a specific value to look at, we have the computed average of the class interval. Now, you've probably noticed that there's a difference in the denominator. The denominator of the sample variance is n minus 1. The denominator of the population is capital N. So, why are we subtracting 1 from the sample denominator? Well, when statisticians do their math, what they observe is that a sample taken from any population ends up underestimating the total number of deviations in the population, which means that it underestimates the variability of a population. Now, a nice benefit of that is when you get a very large sample size, when n is very large, the value that you compute for the variance ends up being very close to the population variance, what I'd like to call the real variance. Now, before we do an example, let's take a look at another measure of variability, the standard deviation. And all that is the square root of the variance. So we just spend a little bit of time looking at the variance, and voila, we take the square root, and we have standard deviation. And by the way, when people tend to talk about statistics, they tend to look at the standard deviation rather than the variance. It makes more intuitive sense to be working with a standard deviation rather than a variance, and you'll get a chance to see that, I hope. So let's recap. We have the average deviation from the mean, which was the absolute magnitude of the deviation, so our deviation ends up being something other than 0. We have the variance, which is going to be the square of the differences. And then we have the standard deviation, which is the square root of the square of those differences. Now, they're all measures of variability of the data, and they all relate to each other. Now, you can probably see how average deviation from the mean feeds into variance, and then of course variance is part of standard deviation. So here we've got two nice examples of data. On the top, we have fluorescence emitted by a certain, I am going to guess that is a fungus, Candida, I imagine. So fluorescence would be the light response, depending on the temperature that this fungus is exposed to. You can see relatively low levels of variability. You get nice smooth curves, and if you look at the data, they probably mean something if you understand what's being measured. Now below we've got annual temperatures from a weather station in one particular location in England, and you can see there's a massive amount of variability. Now, just to give you a hint, I'm not actually going to go into the details on this one, but the bottom graph was used by, I guess they're called climate change deniers, and they are using this as proof that climate change is not real. Now, I think intuitively you probably already recognize the problem of using data from one single location without any context to make some rather broad conclusions, and that's one of the dangers of statistics. You've probably heard the old maximum, more lies in statistics. That's not really true. If you know what you're doing, statistics are truly powerful and they are truly honest. The problem comes in when you have people who intentionally or inadvertently make mistakes. So intentionally making mistakes means you just straight up lie, or unintentionally making them means you don't know what you're doing. So let's compute the variance and standard deviation of some data. Remember our banana computers example? We've got our population data. This time we're looking at it as population data, so we're going to use a slightly different formula. The low value for the end of month stock price was $59, and it ranged all the way up to $74. Now, your task is to, number one, compute the variance, and number two, compute the standard deviation. So, you're going to have to choose a strategy. It's a fairly simple one that we've got here. First of all, you compute the variance. It's pretty obvious that you must compute variance before you compute standard deviation. Second part of your strategy will be to compute standard deviation. Now, we've got our population data. We're going to start off with variance. And the formula we're working with is sigma squared, so variance is the sum of x minus mu squared all over capital N, the population sample size. Now we compute all of our differences, square each one of them, so we get rid of the negative values. So here we've computed the differences, here we've squared them. We end up with positive squares of all these values, and we divide them by the population size, which happens to be 6. We've got a pretty small population. We do our division of a fraction, and we end up with a variance that is 25.3. Now, next step is we're going to compute the standard deviation. Remember that we have a variance of 25.3, and our standard deviation for the population is going to be sigma. So sigma is equal to the square root of sigma squared. We're going back to grade 10, ladies and gentlemen. And here we have 25.3 as our square value. And we conclude by stating that our variance was 25.30, and our standard deviation is $5.03. Now, when you look at your data, you can see you've got 59, 68, 69, 74, 62, 70, and you'll remember that our average, our mean, was $67. So let's take a look at standard deviation. $67 plus $5 would give us $72. And you'll notice there's one data point above that, $74. And let's go on the other end. 67 minus 5 gives you 62. $62. There is one value below $62, which is $59. This fits with the general idea of standard deviation. I do hope later on in the course we'll get a chance to look at this, but typically we talk in terms of 1, 2, and 3 standard deviations from the mean. One standard deviation from the mean covers about 68% of the data. So you could reasonably expect that only about 30-something% of the data falls outside plus or minus your standard deviation from the mean. So you'll hear that a lot. Standard deviation from the mean, 1 standard deviation, 2 standard deviations, and 3 standard deviations from the mean. You can see that variance is not quite as useful in terms of straight up intuitive use. And we have come to the end of our example for the PowerPoint. Let's take a quick look at this. No, we're going to do that with the next video. And I do recommend that you take another look at the content for B7 after watching this video. Hopefully things have been clarified for you. If not, do make sure that you are posting your questions in the discussion section in the class lounge, and you'll notice that there are 3 brand new posts there. So make sure that any questions you have, you post in the class lounge. Thank you for watching,